40 volume of 40 parallelopiped is spanned by these four vectors. Okay, so our main goal of this video would be to find the 40 volume, of course, but we will begin with how we find 2D volumes, 3D volumes, 1D volume, and then go on to the 40. Right, because we will just generalize the thing that we have been doing in the first, second, and third dimensions. And yeah, so now what does 40 volume actually mean? In 3D it makes sense to say volume, right? Now 2D volume, by 2D volume I just mean the area, that if there are two vectors, right, then the area is spanned by the extension of these two vectors on either directions. So this area of the parallelogram is basically the 2D volume, which is just the area. And this parallelogram, 2D parallelopiped is just this parallelogram when each of the vector is shifted on the opposite direction, like this one is shifted over here. And yeah, this parallelogram is just 2D parallelopiped. Basically parallelopiped and volume are like the things of 3D, but yeah, we are just generalizing. And 1D volume will just be a length of line, right? And in this case, the 1D parallelopiped will just be a line because there's just one vector and we can do nothing with it, right? Okay, now let's try to go first with the 2D volume, or let's say 1D volume, right? Now let's say if I have a vector, let's say, now in 1D there can just be one dimension, right? So yeah, so if I have this vector 2, it just means that I have this vector which is basically 2 units long in just one dimension, and that's it. Now to find the in the 1D volume, we just do it, we can just take the magnitude, we can just take the number that we have, right? So it's volume, 1D volume, it's just 2. And we will try to later formalize this argument in a different notion, but for now it's just the number that we have. Now in 2D, so let's say we have one vector over here which is a1, a2, right? So there are 2 dimensions now, or this could have been something different as well. I mean, this could have different orientation like this. Yeah, let's say this is a1, a2, and let's say this is b1, b2. Now how can we find its the parallelogram, the area of the parallelogram is spanned by it, right? Now for that, what we can do is we basically need to multiply the base by the height, right? So this is the height. If this is the base and if this is the height, we just need to multiply these two, right? Now if let's say if the magnitude of this a1, a2 vector, if this is a is the magnitude of these two vectors, right, and b is the magnitude of these two vectors, b is equal to square root of b1 square plus b2 square. If that is the case, and if this height is as, so basically the area will be a times as, right? And if this angle is theta, I can write as b sine theta. So a this I will write multiply by a dot. Okay, a times as, right? So that now that will be a times b sine theta. So this area is given by ab sine theta, right? Now we also know that this magnitude of a, magnitude of b sine theta, this is also the cross product that we have learned in our high school. That this is also the magnitude of the a cross b, right? So from here we see that if we just take the magnitude of these two vectors, and if we just take these two vectors, find the cross product and then take the magnitude, that will also give the area of the parallelogram, right? So yeah, let's try this approach. We know that this also gives the area of parallelogram, but for this we first need to find a vector, we need to find b vector, their magnitudes, right? We need to find magnitude of these two vectors. You also need to find angle between them, and only you can get the area, right? Now let's try this approach. If we try that approach, first of all, to find a vector cross b vector, what we can do is Write I, j, k over here. Now write the a vector, which is a1, a2, there's no k component. Write b vector, which is b1, b2, there's no k component, right? And now this will be I times 0 minus 0 minus j times 0 minus 0 plus k times a1 b2 minus b a1 b2 minus, let me just write it as determinant for now. This will basically be a1 b2 minus a2 b1, but let me just write it as determinant without expanding, times this determinant a1 b1 a2 b2, right? Yeah. Now see that this is just a k vector times, this is not constant, okay, this is k vector or k cap. Basically I can say it as k cap because this is a unit vector. Okay, now k cap times a1 a2 b1 b2, right? Now for this one, if you want to find the magnitude of this cross product, that will just be, since a1 a2 b1 b2 is just a constant, and the constant we will do nothing to it, and then find the magnitude of the k vector, right? So since magnitude of k vector is just 1, because that's unit vector, magnitude of a vector cross b vector in this case will just be determinant of a1 a2 b1 b2, right? So over here we got that for the 2D volume, for the if we are given in a 2 dimension, if we are given any 2 vectors, right, to find the area of the parallelogram, that means to find the area of 2D parallelepiped in 2 dimension, what we can just do is we can take the determinant 2D, we can take the determinant of these vectors a1 a2 b1 b2. We got this idea, right? We can just take the determinant of a1 a2 and b1 b2. So that's what we understood. Now let's go to 3 dimensions. Okay, now in 3 dimensions, let's say we want to find let's say we have 3 different vectors which are pointing at 3 different directions, and so these 2 vectors are basically, let's say they are in xy plane. These 2 vectors a1 a2 a3, now we are in 3 dimension, b1 b2 b3 and c1 c2 c3. Now let's say a vector and b vector, let's say this be a vector, let this be b vector, let this be c vector. Let's say a vector and b vector both are in xy plane. We can just assume that, because even if they are not, we can just rotate our like 3 dimension to make them be in the xy plane, and and c be in any other plane out of the xy, right, in other random. So now in that case, how will we basically try to find the volume of parallelepiped? Now what parallelepiped is, for that, first of all try to complete this parallelogram, right? Now this c vector, now for this c vector, try to move c vector to every edge of the parallelogram. Try to move the c vector to every edge of the parallelogram, and congrats, we have a parallelepiped. Parallelepiped is just a cube or cuboid, but but these lines might not be perpendicular to the surface, right? It's just a cuboid, but these vertical lines can be at some angle with the xy plane. They can be at some angle like 60 degree or any of such angles, right? They need not be exactly perpendicular to the base. Just the like cuboid, but with some like tangential stress at the top, due to which the top is slightly rotated, right? And you get the idea, right? This is just pushed a little bit, something like that is the shape of the parallelepiped usually. Now how do you find the volume of parallelepiped? Now usually for volume, what you can do is, if we find the area of the base, which we know that we can find by finding the a cross b, the magnitude of a cross b will be the area of base, right? This will be the area of base, right? And now, for any, because parallelepiped is also a prism, so we can find its volume by multiplying the base area base with the height. Now its height will be this perpendicular line, right? Perpendicular line from base to the top, right? So yeah, if you multiply by this height, our volume will be the answer. So magnitude of A cross B times the height. Now we don't really know the height, but we do know the magnitude of the this C vector, right? So this line over here, which is I can call as C, the magnitude of C vector, right? C1 is square plus C2 is square plus C3 is square. Now in terms of C vector, if this angle be theta, if this angle that C vector makes with this perpendicular line, so that means if A and B are in xy plane, this line will just be the z axis, right? This line will just be the z axis. If this be x, if this be y, this will just be z, right? Yeah, so that will just be z. I mean, if x is I vector, y is j vector, z will just be the k in the direction of k vector. So yeah, so h is just c times cos theta, right? So our volume will just be a vector cross b vector times now this is basically c cos theta, right? C cos theta. Yeah. Now notice that now notice that over here we have magnitude of A cross B and magnitude of C vector times cos theta, right? And also notice that the the A cross B vector, this A cross B vector will basically be pointing in this Z direction, right? So our A cross B vector, what will the A cross B will give a vector that is perpendicular to both A and B and whose magnitude is equal to the area of parallelogram given by A vector spanned by A vector and B vector, right? So basically the vector that's perpendicular to both A and B is this z axis line, right? So basically over here, right in the z axis, our A vector cross B vector will lie, and this is our C vector, and the angle between them is exactly theta, right? So this is just like u v cos theta, where theta is exactly the angle between u and b, which is true in our case. So we can see that I can again write it as A vector cross B vector dotted with C vector, right? So yeah, so this is basically the expression for volume of 3D parallelepiped, right? And this usually is written as just ABC, and this is basically the symbol for scalar triple product. Scalar triple product means there's a vector product as well as a scalar product, and I can write it like this because both A vector cross B vector dot C and the A vector dotted with B vector cross C will give the same answer. So I'm safe to write it like this because yeah, wherever be the cross product, the answer will be same. So yeah, that's safe to write. Now again, we have found out that this is basically the expression for volume, but we can rewrite this as this expression, right? Now let's try to evaluate this scalar triple product. Now for scalar triple product, we first need to find A cross B and then dot it with C vector, right? So if we do that, what we will get is, first of all, A cross B. To find A cross B, what I can do is ijk A1 A2 A3 B1 B2 B3. This is our A cross B, right? And then this determinant will give us this A cross B vector and dot it with C vector, right? So now if I evaluate this, what I just get is, first of all, if I find the determinant for cross product, this will just be I times determinant of A2 A3 B2 B3 minus J times determinant of
a1 a3 b1 b3 plus k times determinant of a1 a2 b1 b2, right? And now over here, if I dot it with c1 c2 c3 c1 c2 c3, what happens is this c1 c2 c3 will just dot with the previous vector and just multiply with it, right? So basically what will happen is we will have c1 times a2 a3 b2 b3. There, dot product, right? If I have, let's say, u1 u2 u3 dotting with b1 b2 b3, what happens is just u1 b1 plus u2 b2 plus u3 b3, right? So we are just doing that. This is dot product. And then minus c2 times a1 a3 b1 b3 plus c3 times a1 a2 b1 b2, right? Now again, I can definitely write it as c1 c2 c3 and then a1 a2 a3 b1 b2 b3, right? because because if you look at it, this I j k are just replaced by c1 c2 c3, right? So this will obviously be equal to original determinant where I j k are replaced by c1 c2 c3, and that's what I have done, right? And now I can further write this determinant as, now if you know the rule of determinants, if I just change one, like if I just exchange the rows, there will be a negative sign introduced in the determinants, right? So this will be equal to negative of a1 a2 a3 c1 c2 c3 b1 b2 b3. And again, if I again exchange these two, again another negative sign will come, we should cancel this negative sign. So this will be equal to a1 a2 a3 b1 b2 b3 c1 c2 c3. So you saw that even in 3 dimension, the volume is just the determinant, right? So even in 3 dimension, the volume of parallelepiped is just given by the determinant. So we saw that the volume of this parallelepiped is nothing but just the determinant a1, a2, a3, sorry, a3, b1, b2, b3, c1, c2, c3, right? Yeah. Now similarly, notice that not just in the second or third dimension, even in the first dimension, the volume was actually just determinant, right? And and if I have just a single number, like just a1 over here, a vector is just a1. To find determinant, what we just do is just write that number, right? Like we don't need to do anything, right? Yeah. So yeah, we see that in first, second, and third dimension, all of the dimensions, the volume of the n dimension parallelepiped is just. And if you want to like generalize definition of parallelepiped, for if a dimension is more than 2, parallelepiped just means like moving all these vectors so as to create a closed figure. So first of all, using these two vectors, we move them aside. We move this one to 3 different places, this one to 3 different places, again this one to 3 different places. So yeah, we just try to move the vectors so as to create a closed figure. If we are in a like more than 1 dimension, yeah, obviously it's not possible in 1 dimension, but for 2, just try to move the vectors to create a closed figure, and that's what a parallelepiped is. And yeah, so similar, using that definition, we can basically have parallelepiped in any dimension, right? And for in any dimension, the volume of parallelepiped from this generalization, we are not definitely sure, but yeah, there are some rigorous proofs too. But yeah, this is like, this is like somehow enough to convince us that volume of the and the volume, not volume, and dimensional volume, and dimensional volume of and dimensional parallelepiped is just the determinant of a of a matrix where each row is a vector, right? Now it's time to find the 4D volume. So we have, from all this discussion, now we do have the idea that volume will just be the determinant, right? So let's try to find the uh, determinant given by these 4 vectors. It will be long, but yeah, just be with me. We will do it. So this will be the volume. The 4 dimensional volume will be the determinant of And notice that these numbers are Fibonacci numbers 1, 1, 2, 3, 5, 8, 13. Wow, right? That's so nice. I chose them so that they will be linearly independent, right? Yeah, 1, 2, 3, 5, 2, 3, 5, 8, 3, 5, 8, 13. Okay, now let's start from determinant. So we know what to do, right? So 1 times determinant of except these row and column where 1 lies. We will try to find determinant of others. 2, 3, 5, 3, 5, 8, 5, 8, 13. Right? Again, minus sign now. 1 times determinant of except the row and column where we have 1. Right? So that will basically just be 1, 2, 3. This will be there. And then 3, 5, 8. And then 5, 8, 13. After that, plus 2 times determinant of 1, 2, 3, 2, 3, 5, 5, 8, 13. Guys, okay. Guys, you know what? I actually made a mistake by taking the Fibonacci numbers. Cause I know that now definitely they are going to be linearly dependent. I just messed myself because now to check for linear dependence you can also like subtract one of the like row with one of the column with another, and if I subtract this column from here, what I will get is 2, 3, 5, 3, 5, 8, and again 3, 5 minus 3, 2, 8 minus 5, 3, minus 8, 5. And since they are same, they would be linearly dependent. So we see that this vector is just the sum of these two vectors, right? So this is basically just lying in the plane where these two vectors lie. And if this lies in that plane, of course, if all three vectors are in the same plane, they would have zero volume, right? Because there's no height. So yeah, seems like all of them will have zero volume. So all of these determinants will just be zero. So this is a good way to find determinant based on the volume, based on the volume interpretation. Okay. So, anyways, guys, it's my fault, but you do get the idea how to evaluate it, right? Yeah, how to evaluate determinant, and also make sure that you have the alternating signs. You need to have that. Now 1, 2, 3, 2, 3, 5, 3, 5, 8. Just to convince you that when there's linear dependence, the determinant is zero. I will just evaluate this easiest determinant, and yeah. So 1 times 8 times 3 is 24 minus 25, minus 2 times 16 minus 15, right? And then plus 3 times 10 minus 9. So this is minus 1, this is minus 2, this is plus 3. So minus 3 plus 3, it's 0. Similarly, just like over here, just like this going to 0, all of them will go to 0 because all these three vector lie in same plane, and so there will be no volume, right? And 3D determinant is just a volume of these three vectors, right? As I told you earlier. So yeah, so this is just 0. So the 4D volume of these four vectors is just 0. Okay, so this was it. Hope you enjoyed the video. Hope you learned something new. Hope you learned something new about the interpretation of determinant. This will be really helpful to you even in the linear algebra, or even this can also help you interpret the Jacobian matrix in 3D and 2D. This will also help you interpret Jacobian matrix in 3D, 2D, also in linear algebra. Yeah. So this interpretation of determinant as anti-volume of the anti-parallelopiped, that's a really important idea, right? So yeah, you got to know this. and the determinant. This is a really important idea. And the determinant is and the volume of and the parallelopiped. Just like 2D determinant is Bulma parallel, 2D Bulma parallel area parallelogram, 3D whole, yeah. So you got the idea, right? So yeah, so please know this will be helpful, and yeah, keep watching the video. Thanks for watching, and look forward to seeing you in upcoming videos too.